All right, so we're starting off with the current electricity workbook. So, once again, a quick reminder all the definitions will be referring to the learning objectives proposed by the Cambridge. And for the circuit symbols, we'll also refer to the circuit symbols proposed once again by the Cambridge. So, this is basically a document that is shared by their official website, the learning objective or the syllabus outline. So it's just copy pasted from there. So moving on to the very first thing, the previous chapter was static electricity or electrical charges, and in charges in that chapter we were primarily studying the charges that are not moving. That's why we call it static charges, the charges that do not move, the charges that are trapped in the substance. So those that study was called as static electricity. In current electricity, the charges are allowed to move. And this one starts with the definition of current. Once again, I'm repeating, I'll be explaining each and every pointer in terms of the demands of O level physics. So, definition. So, preferably, you should be writing the definition as demanded in the learning objective. So you read out the first one. Define electric current as charge passing a point per unit time. So we'll be defining it in that way, charge passing a point per unit time. Now this same definition can be phrased differently as well. For example, uh, it should be noted and it should be clear that generally in physics when we say per unit time, that can also be represented as rate of change. So if we use the word rate of change, let's say rate of change of charge through a point, that would automatically imply that charge passing through a point per unit time. So rate of change, or rate of change, I should say, rate of change would automatically imply with respect to time, generally, right? Technically, the rate can be with respect to anything. It can be with respect to force, it can be with respect to energy, but for the most part in physics we assume that when we use the word rate of change, it is with respect to time. Then the next thing is the unit of current electric current, sorry. The unit of electric current we study in 7 base quantities, that the unit of current is amperes. A starting the A must be capital because that unit is named after a scientist. So the A should be capital. Matter of fact, all the units in physics that are named after scientists begin with the capital letter. So A should be capital. Amperes is a very large unit of current. And even 1 ampere, it is a significant amount of current. Generally, when we are solving the circuits, the current coming from the batteries, small batteries, 3 volts, 6 volt, 10 volts, the current is not that big. It is measured with a prefix that we call milliampere. So milliampere also represents current. So once again, the unit is same. The unit is ampere. Milliampere is not a different unit. All right, it's just a different representation of the same unit, amperes. So milli is the prefix, and matter of fact, 1 ampere, which is quite a large amount of current, equals to 1000 milliamperes. Then we have the next thing, formula. The formula can be obtained from the very definition itself. First of all, I'm going to write I equals Charge passing through a point per unit time. Per unit time means divided by time. So what do we divide by time? Charge. Charge is represented by Q. So Q over T. This is a formula for current that we have. Quantity is used in formula in this one. The quantity I represents current, electric current. All right. It is recommended that you write current, electric current, because current, the word current, if you read in the dictionary, the word current means the flow, how quickly something changes. Current. So that means the motion. It is related to motion, related to movement. And Q, you can write it as small q or capital Q. It represents charge, and small t represents time. And once again, if you're writing it in terms of the unit, current would be measured in amperes, and charge would be measured in capital C, which is coulombs, and time, the standard unit of time is seconds. So what we can say is, if we increase the number of charges, one factor is it depends on quantity of charges. And generally we define current in terms of electrons, in terms of the negative charges. So I can write quantity of electrons, the number of electrons that are there, that would determine the amount of current, and also the speed by which they are moving. So speed of flow of electrons can be in terms of positive charges as well, but generally we write in terms of electrons. So it depends on two things: the quantity of electrons and the speed of flow of electrons. So for example, previously, let's say we were having that many electrons traveling or flowing to the conductor. If I increase those number of electrons, like in this one, you can see I have increased the number of electrons. Now what happens is the amount of current would also be increased for the conductor on the right side. So for this one, the current, I can safely say the current for this one increases with respect to the flow of current on the left side. Now, what if I don't change the number of electrons? So let's say the number of electrons are same, one. All right, let's assume that here we have these electrons, and what I'm going to do is I'm changing the speed of the electrons. So for speed, I'm just drawing the length of the arrow bigger. So the longer vector, let's assume, represents more velocity of electrons. So A is another one. So we have the same number of electrons, but this time the speed or the velocity of the electrons have been increased. So what we can say is, in this case, once again, the current would have been increased. The number of charges are same, but the speed of the charges is now being increased, and that would increase the amount of current. So you increase one of these two things, or you can increase both of them, and that would result in increase in the amount of current. All right, the next thing is conventional current and electron flow. Electron flow is also known as electronic current. Now previously, I don't want to go to the history, but just a brief narrative is previously the current was assumed, or it was believed to be flowing, to be the flow of the positive charges. Later on, we realized that in most of the metals, which are conductors, the current is mainly due to the motion of free electrons, which is the negative charges. But since previously we used to believe, scientists used to believe that the current is due to the flow of positive charges, so from positive towards the negative side, that kind of current is called as conventional current. Now, the word conventional itself, if you look in the dictionary, the word conventional means traditional. So, traditionally, it was believed that the current is due to the flow of positive charges. That's why we call it traditional or conventional current, right? Now, primarily, once again, the current actually flows from negative towards the positive, because in conductors, the current is there due to the motion of electrons, which are the negative charges. But the convention is from positive to negative. Matter of fact, the bottom line is it doesn't matter whatever direction do you consider, whatever direction you consider. The amount of current at the end of the day would remain same. I mean, if the current in the circuit is 5 amperes, 5 milliamperes, let's say, so no matter if you measure from positive towards the negative or from negative towards the positive, the amount of current would remain 5 milliamperes. It won't change. Now, since here we're discussing the direction of current, and we are saying that current has certain direction from positive towards the negative, and sometimes the student asks me this question: if the current also has a certain direction, why is it not a vector quantity? I mean, all the quantities that have a certain direction are the vector quantities. But the thing is, one of the way to respond to that question is a vector quantity must be having a direction, and the vector quantity should obey the law of addition, the law of vector addition. If something is a vector quantity, for example force, then you should be able to add different forces by vector addition, by head to tail rule, or by the method of parallelogram, or whatever you call tip to tail rule. But with the current is, if you have two or three currents, you cannot add them by any of those method of vector addition. That's why current is not a vector quantity, although it has some direction, I mean from positive to negative, but still, because it does not obey the law of addition of vectors, so that's why it is not a vector quantity. Now here we have a question. So right in the middle we have a battery, and on the left side we have a positive terminal of the battery. Even if it's not marked, you must know that the longer terminal of the battery is a positive one, and the shorter terminal of the battery is a negative one. So if I consider the direction of current from the positive terminal towards the negative terminal, I mean this direction, from the positive all the way towards the negative, which in this case appears to be counterclockwise, that direction would be called as conventional current, because it is from positive towards negative. So that direction would be conventional current. And matter of fact, this is the direction of current that we'll be mostly using, positive to negative. But at the same time, if I consider the direction of current from the negative towards the positive, I mean once I have closed the switch, so from the negative towards the positive, that direction of current would be called as electron flow. electron flow, also called as electronic current, but the term that is used by Cambridge once again for O-level physics syllabus, it is electron flow. So we just stick to that one. The word conventional means traditional. Once again, we stated this fact previously as well. All right, here we have a sample question that is related to the topic that we studied. The electrical circuit shown consists of a cell connected to a resistor. As we move towards the next slides, we'll learn these symbols and we'll practice these components in the circuit as well. This symbol represents resistance or a resistor, which we'll be studying in detail as well. But the question is not about the resistor, it is about the direction of current. What are the directions of the electron flow and of the conventional current in the resistor? Now, the terminals are not marked, but like I said, the longer one represents positive and the shorter one represents negative. So if I try to move from the positive towards the negative, then I'll be following this path. And from the resistor, my path will look something like this, which is counterclockwise in this case. So that would be the direction of conventional current because it's coming from the right side. So the conventional current from the resistor would be towards the right side. So I'm going to discard option B and option C because these two options show that the direction of conventional current is to the left side, which is not the case. And if the direction of conventional current is through the resistor is towards the right side, then the direction of electron flow would obviously be to the left side. And there you can see coming from the negative side towards the positive side, we follow a clockwise direction. So through the resistor, the direction is towards the left for electron flow. So it has to be option D. And the rule of thumb is conventional and electron flow cannot be in the same direction for a same component. Anyway, moving on to the next one. The more the current passing through the wire in 1 second, the bigger the current is. Then we can say that current is the rate of charge flowing. And once again, the rate of charge flowing would be written as I equals to Q over T. Now, how do we know that? Like I said, in physics, whenever we use the word rate of, it means with respect to time or divided by time. And whenever we use the word with respect to time, it means that quantity would be divided by time, unless mentioned otherwise. So we have to use this tradition. Once again, we have to use this convention that the rate of charge means charge with respect to time, unless mentioned otherwise. The electric current flowing in a circuit can be measured by an ammeter. Ammeter is a tool if you want to measure the current experimentally, practically, physically. If you want to measure the amount of current, then you use a tool that is called ammeter. Or these days, we don't have an ammeter explicitly in your science labs. We generally have another tool that is called multimeter. So multimeter consists of ammeter as well. It is multi-operational. You can measure a lot of things with it, 3 things primarily, and current is also one of them. But what is the tool that is used to measure current only? Ammeter. And there's another one as well that is called galvanometer. Here we do not discuss galvanometer in details, but for a side note, I can tell you galvanometer is generally used to detect current. It doesn't tell you how much current is there, how many amperes of current is there. It just tells you if the current is there or not, just like a tester. So galvanometer is just like a tester. It can tell you the direction of current. It can tell you if the current is there or not. If you want to actually measure how much current is there, you use ammeter or multimeter. And the other thing is, which we'll be studying in detail in DC circuits, it is connected in series in a circuit. Why do we connect it in series in a circuit and everything like that we'll be studying in detail in the next chapter, that is DC circuit. The symbol of ammeter. Now you're not going to draw the entire ammeter in the circuit to show there's ammeter. So we have a symbol for it, and the symbol for ammeter is a capital A that is enclosed in a circle. So this is a symbol for ammeter. So whenever you find a symbol like this, it means there's a device called ammeter which is placed there in the circuit to measure the amount of current flowing through the circuit. All right, here we have some of the sample questions. In 10 seconds, example question number 1. In 10 seconds, 60 coulombs of charge flow around the circuit. Calculate the current through the circuit. A bit of spelling mistake here. So first of all, you have to write down the formula. This is a proper way of solving the question for your exam. You write down the formula. Writing down the formula in any way is in most of the cases contains independent mark, and then also it is convenient to do the simplification then. So charge is 60 divided by, in how much time? 10 seconds, and that gives us 6 amperes or 6 amps of the current. That's such a large amount of current. Our body is not able to handle that amount of current for more than a second. Even for less than a second. It's such a high amount of current, 6 amperes. Very dangerous. All right. Example question 2. Sometimes if they're trying to be tricky, if they're trying to play around, so what they'll be doing is the examiner, he'll be messing up the units. He'll be playing with the units. All you have to do is ensure that the current has to be in amperes, which is a standard unit, unless stated otherwise, and the time has to be in seconds, which is a standard unit of time, unless stated otherwise. And what we need to find is the amount of charge. So you write down the formula as it is. I equals to Q over T. Now since you need to find Q, you can make Q the subject. So Q equals to IT. I still tell my students that you can memorize it as quit. Q equals to IT, quit. So Q equals, once again inserting the values here, I is 150 milliamperes. In amperes, that would be 150 divided by 1000, which would be 0.150. In amperes, 150 divided by 1000. Then time has to be in seconds. So 3 minutes equals to 3 times 60 seconds, which is 180. Now all you got to do is hit it on the calculator once again. 180 times 0.150, 27. So the answer that we get for this one is 27 coulombs. Alright, the next thing that we have is alternating current versus direct current, AC versus DC. First of all, we'll be defining it the way that we should be defining in terms of the key terms and the keywords proposed by the Cambridge. So Edison on the left side. So on the left side, I'm going to write about the direct current, DC current. All right. So the left side would be representing DC, and the right side would be representing AC. So for the direct current, we define it as the current that flows in only one direction, or in one direction only. This is how we define the direct current. Then the next thing is alternating current. As the word is giving you the hint, alternating, that means the change. So the current that changes its direction periodically is called alternating current. So the current that changes its direction periodically All right, the word periodically is important here, and it means that the change in direction should be consistent with time. After exactly a fixed amount of time, there should be a change in direction. It's not a random process like the for in the start the current changes its direction 2 times in 1 second, then in the next second it changes the direction 8 times, and then in 16 times. No, it's not like that. Periodically means there should be equal amount of change, equal the the number of times the direction is changed is equal in equal time intervals. Now the next thing is the sources. The primary sources of DC current are cells, batteries, power supply, and in most of the science labs, in your school lab, you must be having a power supply from which you can get a certain amount of voltage. So these are the primary sources of the direct current. Now about the alternating current. The alternating current for the most part are obtained from the generators, to be precise AC generators. The word once again AC here stands for alternating current generators. Yeah, there are DC generators as well, which give you the direct current. So you can write that for the example of direct current. So that is the source, and the primary source of the alternating current is the generators, AC generators. And from the generators, the electricity generated is transmitted to the transmission system. It is distributed. It is there in our sockets, and in all the sockets, for the most part, like 99% of the times, the current electricity that you get from the socket is alternating current. Now the other things about this one is the graph. For the direct current, if we represent the amount of current with respect to time, so we are making a graph of the amount of current, the amperes of current, I measured in amperes. Here also I that would be measured in amperes. I can write over here as well. Current that is measured in amperes, and current that would be measured in amperes. And on the x-axis, I'm going to represent time in seconds. You can cross out this one x, because we have already mentioned the quantity, that is time, on the x-axis. So time on x-axis and current on the y-axis. If I draw the graph of direct current, now the graph of direct current might look something like this. It would be a straight line like this. This one represents direct current. So if I assume that one block, I don't know how clear the block is, but one block is from here till here, right? These are separated by small dotted lines. If one block represents 1 ampere, then the direct current that I have right now is 2 amperes. All right. Once again, it's an assumption that one block represents 1 ampere. But that amount of current, that current would be direct current, because its direction does not change. It was throughout the passage of the time, it was always positive. It is not below the axis. It didn't get below the axis. Or in the second case, there's another example as well. So for instance, there is a current that is represented by a graph like this one. So if we analyze this one, then we'll find out, once again, let's say one block represents 1 ampere. So this one would be minus 1 ampere. But since this current was always negative from the beginning till the time we kept observing the current, it was always negative. It never changed the direction. Whatever its direction was, it is just the same. If it were negative, it is negative. So that current is also direct current, because it was negative and it did not change the direction. It is still negative. And also for the green one, that was positive and it remained positive. It did not change the direction. Now if I compare the currents, so I call this one, let's say this one I'm going to call I2, and this one I'm going to call I1. And if I compare the currents, I can safely say that I1 is greater than I2. I mean, the positive and negative, it won't matter with the current. All we are comparing is their magnitude. Forget about the negative sign. The first current represented by the green graph is 2 amperes, and the lower one represented by the blue graph is 1 ampere. Now the other thing is, it must be kept in mind that the direction of direct current does not change, but the magnitude can change. Now, what do we mean by that? For example, we have a current that looks something like this. All right. So this is a graph of a current that looks something like this. It looks half cycles. Is that direct current? Yes, it is. How do we know this current? With the passage of time, it has always been positive. It did not get on the lower side of the x-axis where it would have been negative. Its magnitude might have been changing from time to time. For example, at this point the current was 0. At this point the current was maximum, Maximum means it would be a positive value. At this point over here, the current would be, if it is 2 amperes, let's say over here, at the point A it is 2 amperes, then at the point B it might be 1 ampere, but the thing is it would always be positive. And then at the point C it would be 0. At the point D it would be once again 2 amperes. At the point E it would once again be 0. At the point F it would once again be 2 amperes. So the value of current is always positive. It is not changing the direction. If it's not getting negative, it means it is not changing the direction. Matter of fact, the negative sign with the current tells you the change in direction. So for this one, we can safely say that it is also representing current that is direct. So just let me raise off these extra ones. All right. Now, with this one, I can also draw another graph. So for instance, the first one is representing I1 above the axis. I'm going to represent the waveform of another kind of current. So for instance, here I'm going to draw another waveform of current that looks like sawtooth. Now for the green one, let's call it I2. For the current I2, all the values of current I2 with respect to time are negative. If they are always negative, it means its direction is not being changed. Whatever the direction is that is being represented by the negative sign, it remains negative. It doesn't change. And if the direction does not change, it means the current would always be direct current. Moving on to the next one, that is alternating current. Now for the alternating current, its direction should change first of all. The key difference is direction should change. How do we represent change in direction? The thing is, it would be having positive as well as the negative values. So I can draw some reference points here. All right, so here we have an example. In this one, you see in the first cycle, this is the first cycle. In the first half of the cycle, I mean in this one portion, the current was on the positive side. The current was positive. It means it was moving in a certain direction. So might be moving from positive terminal towards the negative terminal to the lamp or any appliance. So in the first half cycle, the direction of current would have been this. Show me drawing a battery. In the next half cycle, the direction of current changed. That's why it is negative. It might have been moving to the left side. If the previous direction was towards the right side, in this cycle, in the next half cycle, the direction would have been opposite. So whenever the direction changes, it is alternating current. So this one represents alternating current, and there are some other waveforms as well. For example, this one. These ones are also representing alternating current because their values change from positive to negative or from negative to positive. If it were always positive, it would be direct current. If it were always negative, it would be direct current. But if it is sometimes positive, and after a specific time interval, it changes to positive. After that specific time interval, it changes to positive once again. That would be alternating current. The bottom line is not the bottom line, kind of a side note. The side note is uh, it has been a big debate between two leading scientists, inventors of their times, Thomas Edison and Nikola Tesla. Tesla had worked under the or in the labs of Thomas Edison as well. He was employed by Thomas Edison. Tesla was promoter and advocate of alternating current because he proposed that using the alternating current, it is easy to transfer the electric energy without too much loss. Edison was, however, he used to belong from the other school of thought. He said direct current is less dangerous for the humans and for the animals. Matter of fact, he used to propagate that alternating current is too dangerous, and to demonstrate or to prove his point, he used to electrocute animals. He used to kill animals such as elephants and some other animals just to prove his point. In the end, there are many books written on this topic, the debate and the fight that was there between Thomas Edison and Tesla. But at the end of the day, Tesla won the debate, he won the battle, and the entire system of electricity was based on his prototypes, it was based on his patents and his proposals. Matter of fact, up till now, the electricity that is transmitted is alternating current. Why is that? We'll be studying in the upcoming chapters. What are the advantages and stuff like that. So that was the difference between alternating and current and direct current. Generally, you get 2 mark question in which you have to write the differences, and also in paper 1 you get the graphs in which you have to figure out which one is the direct current and which one is the alternating current.